Hey everyone, welcome to 8.2. Today we're going to be talking about properties of rational exponents. So just as a reminder for this section, you're still going to need to know properties of just general exponents that we talked about at the beginning of chapter 7. So hopefully you have all those rules written down. If you don't remember those those exponent rules, you need to go back and maybe rewatch the very beginning of chapter 7's video to go through those. So I'm just going to go through one example really quickly, and then we're going to start talking about rational exponents. So just remember, with exponents, we might have something like this: 2 to the 5th over 2 to the 8th. And remember, if we're dividing exponents and they have the same base, then we can subtract the exponents. So we have 2 to the 5 minus 8, which gets us 2 to the negative 3. And then remember, we talked about how we don't want to leave negative exponents in our answer. So if we have a negative exponent, then it actually moves to the denominator. So we'd have 1 over 2 to the positive 3. And then this one is when you can go ahead and simplify. 2 to the third is going to get us 8. So 2 to the third is 8. So we get 1/8 as our final answer. Okay, and obviously if you have variables, you would stop go as far as you can and then stop. This is one that has all numbers, so we get a number answer. Okay, so this is just one of the rules that we've talked about. Like I said, go back and review those if you think you need to. But today we're going to be talking about rational exponents. So rational exponents, we're now going to start seeing fractions in those exponents rather than all whole numbers. So an example might look something like this: 5 to the 1/2 times 5 to the 1/4. Now remember, when we multiply something with like bases, then that means we add the exponents. So we'd really have 5 to the 1/2 plus 1/4. And then you have to think about adding fractions. So yes, you're going to have to get comfortable with fractions. Remember, in order to add fractions, they have to have the same denominator. So 1/2 is the same as 2/4. So really this would be like having 5 to the 2/4 and then plus 1/4. And when we add those together, we get 5 to the 3/4. And then we practiced in the last section if they wanted you to convert it to its radical form. Remember, this is the root and the top number is the exponent. So this would convert to the 4th root of 5 to the 3rd. Now, I'm not going to ask you to do that much in this section, but just as a reminder of what we talked about in the last section. Okay, so 5 to the 3/4 is our final answer. We can also have an example that looks like this: 2 to the 4th times 3 to the 4th, all to the negative 1/4. So there's a couple different ways you could approach this problem. You could distribute the exponents if you wanted, but because these have similar exponents, we can go ahead and combine our bases. So this is a little bit different than example 1, because obviously 2 and 3 are not the same, but we have matching exponents. So if we multiply our bases here, we get 6 to the 4th. Now we can only do that because the exponents match. Okay, so we get 6 to the 4th all to the negative 1/4. And now we have a power to a power. So remember, powers to powers, we multiply. So when we take 4 times negative 1/4, we get 6 to the negative 1st. And then back to our negative exponent rule, remember, we don't leave those, so we flip it. So we get 1 over 6 to the 1st, or just 1/6. Okay, so it's the same rules that we've used in chapter 7, but now we're just dealing with fractions, and so it makes it a little bit more complicated. Okay, once we've dealt with the basics, then we're going to start getting into seeing some radicals. So let's say I have example 3 here. Maybe I give you the cube root of 4 times the cube root of 16. So remember, roots can be written as exponents. So this would be the same as saying 4 to the 1/3 times 16 to the 1/3. And remember, we just talked about how if the exponents match, we can multiply the bases. So what I'm going to go ahead and do is multiply my bases together. So if I multiply, I get the cube root of 4 times 16, which gets us the cube root of 64. And then you always want to see if you can simplify. So is there something to the third that will get us 64? Well, in this case, that's 4. So 4 times 4 times 4 is 64. So there's our final answer. Okay, so notice if I have the same roots, I can multiply the numbers together, and then I can simplify from there. So let's look at example 4. This one is actually working backwards. It's going to tell you to simplify. And I would have the cube root of 54. So in this example, obviously we don't have a number to the third that will get us 54. So they don't want a decimal answer here. They want it to be in its simplified radical form. So in order to do this, we have to first think about all of our cube roots and see which number that it's a cube root would go into 54 evenly. So if you don't know your cube roots off the top of your head, it wouldn't hurt to write them on your paper or in your notes somewhere because you're going to use them quite a bit. So the cube roots would be something like 1 to the third is 1, so 1 is a cube root. 2 to the third is 8, so 8 is a cube root. 3 to the third is 27, okay, and then we continue going 4 to the third, and we get those numbers on the right to be our cube roots. So you want to see if any of these numbers, 1, 8, 27, etc., if any of those go into 54 evenly. Well, 27 does, so what we could do is break this up into the cube root of 27 times the cube root of what? Well, 27 times 2 gets us 54. So it's kind of like what we did with square roots, but now we're having to think of cube roots instead. And this works for fourth roots, fifth roots, etc. So what is the cube root of 27? Well, we said 3 to the third is 27, so the cube root of 27 is 3. And you can't take the cube root of 2, so we just have 3 times the cube root of 2. So there's our simplified answer. So notice we broke it up just like we did square roots, and then we simplified as much as we could. Okay. And what about this example here, example 5? So we'd have the fifth root of 3/4. Well, there's no number to the fifth power that will get us this fraction, so that's a nice number. So we have to think back to what we've done in the past with our exponent rules. If we have a fraction, we split it up. So I'm going to have the fifth root of 3 over the fifth root of 4. Well, that still doesn't help us because we can't take the fifth root of 4 or the fifth root of 3. And remember, we don't want to have radicals in our denominator or fractions. So we have to somehow simplify this. So we have to think of our fifth roots. Okay, so the 1 to the fifth is 1. Okay, and then we can do 2 to the fifth is 32. 3 to the fifth is 243. So does 4 go into any of these evenly? Well, we can take these numbers and we notice that 32, okay, you can get 4 times something to get us 32. So what we're going to do is we're going to multiply the top and the bottom by a fifth root of some number that will make the denominator simplify nicely. Okay, so right now it doesn't simplify, but we want to multiply it by the fifth root of something to get one of our fifth roots that are perfect. So 4 times what gets us 32? Well, 4 times 8. So we're going to multiply the top and the bottom by the fifth root of 8. And then we're just going to go ahead and simplify. So when I do that, I multiply across, so I get the fifth root of 24 on the top. And then I multiply my roots down on the bottom, so I get the fifth root of 32. And now this is something that can simplify nicely. So we can't simplify the fifth root of 24, but that's okay because it's in the top. Okay, but what is the fifth root of 32? Well, that's 2. So we get the fifth root of 24 over 2. And now it's in its simplified form, and then we'd be done. And notice there's no numbers you can break 24 down into that have fifth roots. That's why we have to leave it on the top, unlike example 4 where we could break it into something that's simplified. So sometimes you're going to be able to break them down, and sometimes you won't. The more you practice knowing your roots, the easier and quicker this will be. Right? And the last few things I want to talk about are when you're adding and subtracting radicals, and then we're going to practice simplifying radicals that have variables in them. So let's say I give you, let's see, this was example 6, something like this, the cube root of 16 minus the cube root of 2. Well, we know that they have the same roots, but they're not being multiplied or divided, so we have to deal with this a little bit differently. If you're adding or subtracting, okay, so this is for adding and subtracting, you have to have the same number underneath the root. Okay, so that's very important. So must have same number under the root. Very important, okay? So in order to simplify this at all, we have to think of if we can break down the cube root of 16 so that in its simplified form it has a cube root of 2 in it. Well, remember we talked about what our cube roots were. We said 1 was a cube root, 8 was a cube root, 27 was a cube root. Well, can any of these go into 16? Well, 8 can. So I'm going to break this down into the cube root of 8 times the cube root of 2. And what is the cube root of 8? Well, that's 2. So we get 2 times the cube root of 2. And then I'm just going to bring down my cube root of 2 that I had down here. So minus cube root of 2. And notice now they both have the same cube roots with a 2 in them. So now I can subtract. And just think of this number out in front as being a 1. Okay, even though there's no number technically there, it's a 1. So we're going to have 2 minus 1. Well, that's 1. And then we have the cube roots that stay the same. So kind of think of them as variables. Okay, those aren't going to go away. You're just going to subtract the front numbers. Okay, so 2 minus 1 is 1, and then we keep the cube root of 2 at the end. All right, so let's try example 7, a similar concept. So this example gives us 2 times the 4th root of 176 plus 5 times the 4th root of 11. So just like the last example, notice we don't have the same roots. So the goal is to get down to a matching root. And in this case, we want to try to get down to the 4 root 11. So can we break down 176 so that it has a cube root or 4th root of 11? Well, easy way to check this is, can you divide 176 by 11? Well, when you do, you get, let's see, 16. Okay. So what this means is this can be broken into the 4th root of 16 times the 4th root of 11. And when we simplify that, can you take the 4th root of 16? Well, what to the 4th gets us 16? That's a 2. So we get 2 times the 4th root of 11. So I'm just breaking this down. And notice there's still a 2 out in front, so I need to bring that down as well. So I'm going to have a 2 here. So what's 2 times 2? Well, that gets us 4. So this whole first part gets us 4 times the 4th root of 11. And then I'm going to go ahead and bring down this here, so plus 5 times the 4th root of 11. And now because my roots match, I can add the numbers in front. So what is 4 plus 5? Well, that's going to get us 9, and then we keep our root 11, so 4th root of 11. So there's our final answer. Okay, so notice I had to make them match, and then I just add the numbers that are in front, or subtract the numbers that are in front. So if you have any questions on those, make sure you let me know. And the last examples that we're going to go through today are if you're going to simplify roots that have variables in them. So let's look at our first example here with variables and numbers. It says you have the cube root of 125x to the 6th. So when you have multiple numbers and variables underneath a root, you have to look at them separately. So what I'm going to do first is take the cube root of 125. So hopefully as you're getting more familiar with cube roots, it's easier to identify those answers. So what to the 3rd gets us 125? Well, that's going to be 5. Okay, and then we have to deal with the variables. So the easiest way that I usually tell people to do this is to think about dividing. So if I take the exponent of the variable, 6, and I divide it by my index, 3, so 6 divided by 3, what's that get us? 2. So that tells me that I'm going to have an x to the 2nd. And then there's my final answer. Okay, so all I did was divide the exponent divided by the root, and then I solved. So let's try this with example 9, because example 9 is a little bit different. So this one, I have no numbers, I just have exponents with variables. So I'm going to do the same concept that I did with the example 8, where I had x to the 6th. So I'm going to start by dealing with the x's first. So I'm going to take 6 divided by 4. Okay, so the problem here is that 4 doesn't go into 6 evenly, so I'm going to have a remainder, and I'll show you what to do with that. So how many times does 4 go into 6? Once, and with a remainder of 2, okay, because 4 times 1 is 4, plus 2 gets us 6. So what this tells us is how many are going to go on the outside, and how many are going to be left underneath my root. So the way I'm going to write this is I'm going to have 1x on the outside, because that's the 1, and then I'm going to have a 4th root still, with 2 x's underneath, so an x squared. Okay, and then I'm going to do the same thing for each letter. So I'm going to take my 4 and divide it by 4. So 4 divided by 4 is 1. Notice there's no remainder, so on the outside I'm just going to have a y to the 1st, and no y's underneath because there was no remainder. Okay, and then I'm going to do the same thing for the z's. So I have a 15 divided by 4. So 15 divided by 4. 4 goes into 15 3 times, that's 12, with a remainder of 3. So this is going to tell us that we're going to have 3 z's on the outside, so z to the 3rd, with 3 z's left over on the inside. Okay, so this right here is our final answer. So notice you have some variables on the outside and some variables that are left over that couldn't be simplified any further. And same concept for example 10, just now we have a fraction. So this actually combines what we talked about earlier with rationalizing a denominator as well as simplifying those exponents. So I'm going to go ahead and start by breaking this up into two different parts. So I'm going to have the cube root of x to the third over the cube root of y squared. And hopefully you can see right away that the top is going to simplify pretty quickly. 3 divided by 3 is just going to get you a 1. So we're going to have an x to the first on the top. But the problem with the denominator is that you can't take 2 divided by 3. 3 doesn't go into 2. So this is a problem. So what that means is that I need to multiply the top and the bottom by something so that my denominator will simplify. Because remember, we can't leave a root in a denominator. So how many more y's do I need in order to make 3 go into it evenly? Well, I already have 2, so if I have one more y, so a cube root of y to the first on the top and bottom, then that's going to make my denominator go away. So when I do that, I'm going to get on the top x times the cube root of y to the first, and then when I multiply these two things together, I get the cube root of y to the third, because remember we add our exponents, and now that allows my denominator to simplify. So what's 3 divided by 3? Well, that's 1. So I'm going to be just left with a y on the bottom, and I can't simplify anything here because 3 doesn't go into 1, so I'm going to be left with x times the cube root of y to the first. So right here, even though it doesn't look very pretty, that is my simplified answer, getting rid of the radical in the denominator. All right, so remember when you're doing these problems with the variables, you want to take the exponent divided by the root and simplify as much as you can. All right, so this is it for this section. I know that's a lot of different examples, a lot of rules to follow, but the more you practice it, I promise the easier it will get. I mean, if you need any help, extra help, make sure you take a look at those extra resources on Weebly. All right, thanks for listening.